Hello, everyone, and welcome to our next lesson. This is Unit 4, Ionic Bonding and Nomenclature, and it corresponds to Chapters 7 and 9 in the textbook. So we're going to get started here right away on some properties of ionic compounds. And while you're writing this down, I just want to kind of talk about where we are in the year. We've been learning about atoms, and we've learned about the differences between different types of atoms on the periodic table. We know some elements like to gain electrons and some elements lose electrons. And now we want to talk about compounds here. So these are substances that are going to have two different types of atoms combining together to form a compound. So ionic compounds, again, we said we have elements of different charges here. They're made up of what we call formula units, which means a ratio of positive to negative ions in an ionic compound. Now, for instance, the compound I'm looking at is NaCl in the picture here. So the ratio is 1 Na for every 1 chlorine, but I don't want you to think that there are molecules formed where you just have 1 Na and 1 Cl going off on a date by themselves, so to speak. Na and Cl, Na has a positive charge. So if we look here in the key, the gray molecule, or the gray atom, is sodium. And it has a positive charge, which means it's attracted to negative charges on all sides. Once it has given up its electron to one of the chlorine atoms, that chlorine is negative, this sodium is positive, but then this other negative chlorine is attracted to sodium. So is this one down here. So is this, so is this, so is this. So every sodium atom is actually surrounded by 6 chlorines if you count those up. And if you can imagine this picture going on longer, you would visualize every chlorine surrounded by 6 sodiums and every sodium surrounded by 6 chlorines. And that's exactly what would happen. And this block would go on in 3 dimensions for billions of atoms. And that's what a crystalline solid is, a solid with a repeating 3D pattern of positive and negative ions. So I want you to understand when we talk about the properties of ionic compounds, they come from the structure that we're seeing here. So these tend to be very stable compounds. They have high melting points. Each ionic compound has a coordination number, and that is the number of oppositely charged ions which surround an atom in a crystal. We won't talk much about coordination numbers, but if we went back to the example on the previous page with NaCl, the coordination number would be 6 because the sodium is surrounded by 6 chlorine atoms there. And ionic compounds tend to be good electrical conductors when melted or dissolved in water. Now I just want to look down here. If you see this molecule, there's a whole field of chemistry, inorganic chemistry, that really deals with the structure of different molecules. And you would learn if you took that course in college about body-centered cubic and face-centered cubic. So I wanted to give you a little background information about kind of what a coordination number is and how these structures would look. But you don't really need to know anything about this for the test that we're going to take. So that kind of covers coordination numbers. As far as understanding their properties, though, I want to go back to the NaCl. The reason that these molecules are very stable and very strong is because it's not just one bond that would need to be broken, but if you want to melt salt, you have to break all of these bonds all throughout NaCl's structure. If you want to break NaCl, and you try to hit this with a hammer, you can imagine that force is distributed to all of these bonds. So it's crystalline solids like this tend to be very brittle, where you hit them and they won't break, and then boom, they shatter apart, because if you break it, you're going to be breaking all of these bonds. And additionally, they're good electrical conductors, it says, when melted or dissolved. So if we think about this here, if I put salt with water, the water will actually pull one by one these atoms away from the structure because water is polar as well. We'll talk more about that at the end of the year, but so these compounds tend to conduct when they are dissolved in water, not as a solid. We're going to take a look here then at metals as well, and so I want to contrast metals from ionic compounds. Metals also form crystal structures, but here the metal nuclei line up closely together and they share a common sea of electrons. So in the previous example with the ionic compound, you have a cation and an anion, and the chlorine is going to take electrons from the sodium. In a metal compound, you do not have an anion, so the electrons are not very strongly held by these metals, and so they end up just kind of floating away from the atoms a little bit and creating a sea of electrons. This allows these structures to be excellent conductors when they're still in their solid form. They don't need to be dissolved or melted. These compounds have electrons that are loosely held, and if we can run a current through those electrons, now we have electricity flowing. So a great example of this, and everyone's got a crystalline metal structure on them, probably copper, because you mostly have headphones in right now, and those are made of a little copper wire, and we get electricity running through that wire. Now, an alloy is something else we need to talk about, and that's a mixture of two or more elements, usually two metals. And when you mix the metals together, it typically leads to some desirable properties. Some examples here, we have our sterling silver versus silver. The sterling silver is less likely to corrode. Steel versus iron, the steel is stronger, sometimes less reactive. So whatever we're trying to accomplish, sometimes an alloy can be effective. I want to show a little video clip here to really give us a great picture of the structures. So
I'm here because they're about to cast several bells. Even with all the other modern materials available, they still choose bronze. I want to know why. Hasn't something better come along after all these years? Ralph Young offers to make the case for bronze.
This is our pattern that we're going to use to actually make the form in the sand.
So this looks like a finished bell. This isn't a bell?
Yes, it does. This is just the pattern, yes. It's made out of aluminum, so it's real easy to handle.
Well, what's wrong with it? Aluminum's good. Aluminum doesn't rust. Aluminum's light.
You're right.
Why don't you make the bells out of this?
Well, the sound. It doesn't have that lasting ring, and it's
You don't like how that sounds?
Not really. It sounds kind of tinny also.
Thanks a lot, buddy.
Yeah, well, you know.
I practiced.
We'll show you what a real bell sounds like.
The quality of the sound depends on the atomic structure of the material. In pure metals, the atoms are arranged in orderly rows and columns. Each atom gives up some of its electrons to create a kind of sea of these randomly moving charged particles.
So this is exactly what I'm talking about here. We have these copper atoms all lined up. They don't have a great hold on their electrons, so the electrons are kind of floating around more freely.
It's these free-flowing electrons that make metals conductive. When placed in a circuit, the negatively charged particles line up and flow as an electric current.
It's important to note that the metal isn't creating the electricity. It's just allowing the electricity to flow through it. So that's why it makes a great wire. We still need a battery, power source of some sort, but we can just run the electricity through here.
The sea of electrons also creates flexible metallic bonds among the atoms. In copper, they can slide past each other easily, which makes it relatively soft and easy to dent. Not right for a bell. That's why Verdon uses stiffer stuff.
So we'll put this down into here.
All right, so we won't watch them make the bell, but we are going to try to fast forward a little bit.
Why couldn't you use one of those metals by themselves? Why don't you make bells out of just copper?
If it was all copper, it would first of all be too soft, and we wouldn't get that sound that we want from a bell. Tin with copper gives us that hardness.
Adding tin to copper during melting changes the properties of the metal. The larger tin atoms restrict the movement of the copper atoms, making the material harder. A blow causes the atoms to vibrate, but the tin prevents them from moving too far out of position.
So I just want to talk about what we saw here. In order to make an alloy, you have to melt both of the metals, and then you have to you just mix them together and allow them to cool in just the right proportion. And that's what we have here. They're showing, you have the larger tin atoms, the smaller copper atoms, and so this really looks actually really similar to an ionic compound. The difference is there's no specific anion to hold on to the electrons. And we have just the right ratio here to give it a little strength, but not too much.
Tin is good for a bell, but only in the right proportion. This is what can happen if the amount of tin isn't right.
So obviously there, the Liberty Bell shown with its crack because it seems to have too much tin in the bell, which created too hard of a material that cracked. So we're going to move back to our lesson here on ionic compounds. So we've looked at some structural stuff for ionic compounds, metals, and alloys. So you guys know that. And then we're going to move into a little bit focus on valence electrons, and we'll get back to our ionic compounds, which are main portion of the unit. So we really want to have a good understanding of how ionic compounds are different from metallic compounds and alloys. Now, valence electrons are the electrons in the outermost shell. These determine the bonding that elements have. We know that the group A elements, the group number equals the number of valence electrons. So that means for group 1 with sodium, they have 1 valence electron. We refer to group 6A with oxygen as having 6 valence electrons. Sometimes you might call that group 16. You just have to remember, it's going to be fewer valence electrons because we don't count the D electrons. I'm going to have us quickly draw dot structures for the next 3 atoms here. Hydrogen should have 1 valence electron, so I'm trying to give that dot there. Calcium has 2 valence electrons, so we draw 1 dot on the 2 different sides. And then oxygen has 1, that didn't go well. It should be 1, 2, 3, 4, 5, 6 dots. My drawing not the best there. I just want to be clear that we want to have 2 dots on each of the sides. So I have 2 on the right, 2 on the bottom, 1 on the left, and 1 on the top. And so the octet rule tells us that atoms are going to bond in order to gain a filled outer shell of electrons, 8 electrons. We covered this very well in the last unit, really the last couple of units. So now we're going to look at binary ionic compounds. These will be the easier compounds for us to work with. There'll be some harder examples that we'll do tomorrow. But with binary ionic compounds, we want to keep in mind the cation name stays the same. The anion ends in "ide." And then we're going to use this flip and drop method, which I'm about to teach you. In order to write chemical formulas, which we're going to do now, you have to know the charges that elements take on. So potassium, sorry about that. Potassium has a charge of +1, so it's K with a +1 charge. Oxide has a charge of -2. We've been going over this because of the columns that they're in. Potassium's in column 1, it gives up 1 electron. Oxygen in column 6 wants to move over to column 8, it takes 2 electrons. You absolutely have to know the charges to pass this test. I know that it's annoying, but you just have to know. So then we are going to do the flip and drop method. We are going to put the 2 over on the potassium here, but this will look like this with K2O. We get rid of the charges. I don't care how many, I don't need the negative there. What the number is telling me here is that there are going to be 2 potassiums for every 1 oxygen. And sometimes we can draw dot diagrams for ourselves here. So I'm going to do that up top. 1, 2, 3, 4, 5, 6 dots on the oxygen. The potassium has 1 dot. The potassium will give that dot to oxygen. The potassium's happy, but oxygen still needs another electron. Where is it going to get that from? From the other potassium atom. So that's what the K2O is telling me, and we can always use the charges, and we can flip them and drop them. We get rid of the charges, we get rid of the ones. We have K2O in the first example. And in the second example, lithium has a charge of +1 from its column. nitride. Remember, this is -3. Nitrate and nitrite are that exception, but nitride is just N-3. Now we flip and drop, and we end up with Li3N. We need 3 lithiums to give nitrogen their valence electrons. Nitrogen moves from 5 valence electrons to 8, and this is the answer for lithium nitride. Now, on the next problem here, still another easy one, but we have Fe+2. The Roman numeral for these elements tells you the charge. That seems pretty easy, I think, for us to remember, but I promise you I'm going to have a lot of people getting this wrong on the test. So Fe is +2, sulfide, that's S-2. We are going to flip and drop, and so now we have Fe2S2, but wait a minute, we need the lowest whole number ratio, so we can reduce those 2's and we get FeS as the lowest ratio. So a lot of times if we're looking at this compound, we'll be able to go in reverse, and a lot of people might call this Fe1S because they think the Roman numeral is telling me how many iron atoms there are, but it in fact is telling me the charge of that iron atom. And then the last example here is tin, which is Sn+4. The Roman numeral tells me the charge. Selenide, Se is -2. And then we are going to crisscross and get Sn. I'll put the 2 here. Se4, just so I can show you that those reduce to Sn, Se2. Tin 4 selenide. So for these types of problems, the compounds, the charges will either be coming from the columns that the elements are in, or they'll be coming from the Roman numerals. But remember all those hard ions that I made you memorize the other day? Those will be back tomorrow. So if you haven't memorized all your ions, please get to work on doing that. And then you can take a look at the assignment for tonight, and we will see you tomorrow. All right, so on the last slide, we were given the names and asked to write the formulas, and we used the flip and drop method. On this slide, we're going to be asked to write the names of the compounds based on the formula that we're given. So the first rule is that we're going to write the name of the metal regularly, and then the non-metal with the IDE ending. And if we have a transition metal used, the second rule tells us we have to show the charge with a Roman numeral. So in the first example here, I have CaCl2. We don't have to worry too much about anything here because we know that Ca is calcium and we know that Cl is chloride, and that's all we have to do with the naming. Here we have MgO, it's the same thing. Magnesium is the cation, oxide is the anion, so we just combine those together. In a problem like this with Cu2O, these can be a little bit more difficult here. We don't know the charge of copper. It's a transition metal. It can have a charge of +1 or +2. We do know that oxide is the anion, so we know the ending will be an oxide. What I like to think about here is that I have O with a charge of -2, and there's only one oxygen here. So all of the anions have a total charge of -2. That means that the cation side has to have a total charge of +2. But there are 2 copper atoms, so we split up that +2 charge to the 2 copper atoms, and each copper would have a charge of +1. So the name is then copper-1 oxide. We have PbI4. This is the same type of problem as before, so I'm going to have you try to solve it. And then I'm going to explain this one here. The I is -1 charge, and there's 4 of those. So that gives us a total -4 charge from the anion side. That means the cation side has to have a total of +4. And so there's only one lead atom here, so the charge on that lead atom has to be 4 plus 4, so it's lead 4 iodide. So in all of these compounds, they all have to be neutral. That's what we learned on the previous slide. And so now we've developed a name for that neutrally charged compound. And last but not least, we have tin. We also don't know tin's charge. It could be plus 2 or plus 4. Oxygen oxide is -2. There's 2 of them, so that's a total of -4 charge. It means we have to have a total of positive 4 charge on the other side. And so the answer is tin 4. Should say oxide here. Tin 4 oxide would be the answer. So that's where we're going to leave off today. We've looked at kind of some of our easier compounds here. We call that binary nomenclature. We will get to the ternary nomenclature tomorrow. So I appreciate you following along here today. Please make sure to complete any assignments with this video. And we will move forward tomorrow, as I said, with the ternary naming.